The photoelectric effect is one of the most important experiments within physics. People think that Einstein won his Nobel Prize for relativity, but actually it was for explaining and using the photoelectric effect to explain the nature of light. We're going to go through the experiment. And I'm going to tell you that the actual experiment itself, you're going to have to understand fully. You're going to have to understand the math behind it. You're going to have to understand like how the experimental setup was done. We're going to get into that. But first, I think it's a little bit overwhelming to learn all that math right away. So I'm going to explain the experiment without mathematics so you get the idea of what they really did and also why it was so important to them. So we've talked about how light is a wave, and we've provided evidence for that. Then we saw that ultraviolet catastrophe, where people were like, wait a minute, these black bodies aren't really acting the way we expect them to. The photoelectric effect is going to fall into that second category. It's going to suggest light isn't a wave, which again, huge parts of physics have already confirmed light's a wave. So getting to be stressful. Let me explain why this idea sort of showed the photoelectric effect wasn't a wave. So if you have a particular surface of material, let's say we had like a metal surface here. Whoa, I don't know why I drew that on a slant. I'm really tired, guys. Let's try that again. Okay, so let's say we have a metal surface. Now on the metal surface, if we were to kind of zoom in, we have all these atoms, which in a very simplified and completely wrong image, we have a proton, we have several protons at the center. And I moved this over here because it's a little easier to see. We have protons at the center and we have electrons going around the outside. Now that is totally scientifically wrong. I'm just going to say that right now. That is called the planetary model. It's much more complicated than that, but we're going to use this idea just to further our explanation. Okay, also my picture is pretty bad. The electrons are actually kind of interacting with each other, but it's kind of fun to watch. Anyway, so if you wanted to knock one of these electrons off the outside, it would take a little bit of work to do that. If you were to come around and smash some energy into this atom and knock one of the outer electrons off, that takes some energy. That type of energy is called the work function. Okay, so in other words, the work function is what's required to sort of knock an electron off the atom. The symbol for the work function is this. And because we're talking about really, really, really tiny things here, we're going to be using that electron volts that we covered previously because it's such a small amount of energy. So if you were to come along and hit this atom with the right amount of electron volts, you can knock one of these outer electrons off. Okay, so as long as you were to give enough energy to one of these atoms, as long as you gave enough energy to sort of match that work function or greater, you should be able to get a little electron flying off the atom. Great, good plan. So what they did was they took light and they're like, okay, light has energy, light gives energy, light is a wave, let's send it down on here. So they send down light, boop, 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 boop. And now the electrons came off. And they're like, well, that's weird. Okay, we must just not be sending down enough light. So they sent down a higher intensity light. In other words, more light of the same frequency. So they're sending down a ton of light and they're still seeing nothing come off. And that was pretty freaky. Let me explain why that's pretty freaky. Okay, I'm going to use an analogy to explain this. So imagine this is all of you in AP Physics. Hang on, let me correct that. Here you are. You're all sad because you're in AP Physics. And you're just desperately waiting to get out of the depression that is AP Physics. So, okay, so now you should be able to recognize yourself. There's you sad. And I come along and I'm like, hey, you know what? I will let you out of this class. And here's the door. You can get out. And this is me. Side ponytail, side braid, inherently evil, standing here at the door, guarding it. And I'm like, I will let you out of this class. Ubiquitous dress. Okay, weird shoes. Okay, so I'm like, I will let you out of this classroom if you will just pay me $5. Not only will I let you out, I will give you an A in this class. And that would make you all pretty happy. You'd be pretty stoked. That life would be looking better. So now let's say that there was coins being poured down. Little, dimes and quarters coming down on you. Tons of them, or maybe a few at first. And I'm like, why are they not scooping up the coins and paying the $5? So I sent down even more, tons more. And you guys still didn't pick them up. In fact, it wouldn't matter how much money I sent down, you didn't pick it up and just leave. That's basically what was happening with the photoelectric effect. You had these electrons who, if they had enough energy coming into them, should have been able to leave. Should have gone flying off of this material. Instead, no matter how much energy you sent down, if it was in this smaller amount, this low frequency, none of the electrons broke off. They just stayed put, no matter how much low frequency energy you shot down on it. To the scientists at the time, they're like, well, that doesn't make any sense. If you have a wave just washing energy in and washing energy in and washing energy in, the electron should get enough energy to pop off. So now, imagine that the scientists sent down a higher frequency light. They didn't send down a lot of intensity, so not much of it, but it was a higher frequency. And again, I'm using blue just to remind you, because even though we think of blue as being a calming color, as red as being very energetic, remember that blue is actually higher energy. So, and we can tell that because HF is equal to the energy. So the higher the frequency, the higher the energy. And that H is Planck's constant, and that is 6.63 times 10 to negative 34. But you don't have to worry about memorizing that right now. We're going to get into that in a lot more detail in the next section. So anyway, they're sending down high frequency light, not a ton of it, but some. And as soon as they start sending this down, they start seeing electrons popping off this stuff, which is weird. Great and weird. Because to them, it's like, okay, why do we need a certain frequency in order to get these electrons to pop off? In our scenario here, it's as though, we poured down pennies and dimes and whatever, nobody leaves. And then the second we start sending down, $5 bills, all of a sudden people are just leaving the classroom in droves, okay? So we're like, well, that means it doesn't matter how much energy it comes down. It matters literally how much the amount, like the type of energy coming in is. And to scientists, that strongly suggests that light is quantized. In other words, that there is a certain quantity of light that light can possess at different frequencies that it can't possess at other frequencies. In other words, this suggests that there is a certain particle to light. So in other words, because there's these different amounts coming, light probably is a particle. So now scientists are starting to get kind of creeped out. We have the wave stuff with the double slit. Clearly, light is a wave. Then we start to have the black body radiation problem, and they're like, okay, why is light not acting like a wave? And then this comes along, and suddenly like, wait a minute, there has to be a certain set amount of light coming with a frequency that suggests that light is a particle. And everybody is just freaking out. Okay, so now scientists are freaking out. They're like, why is this happening? And what's going to happen is we're going to look at what Einstein was writing about, which is thinking of light as both a particle and a wave, which is going to get interesting, to say the least. But right now we're going to pause. Now, I've done a big overview of kind of what this experiment was and why it felt like the way it did. What we're going to do is now we have to go back and kind of look at the math. So I'm going to walk you through step by step how to sort of do the math of this, okay? So you're probably going to want to watch that in the next section.